Quantum computing is a new kind of computing that uses the principles of quantum physics, which is the science that explains how very tiny particles like atoms and electrons behave. Unlike regular computers that use bits, which are zeros and ones, quantum computers use something called qubits. These qubits can represent 0, 1, or both at the same time, which gives quantum computers a completely different way of processing information. In traditional computing, every operation is done step by step using binary logic. This means a computer must test possibilities one after another. In quantum computing, qubits can explore many possibilities at once because of a property called superposition. This allows quantum computers to solve certain types of problems much faster than classical computers. Another key idea in quantum computing is entanglement. When qubits become entangled, the state of one qubit becomes directly linked to the state of another, even if they are far apart. This connection helps quantum computers perform coordinated calculations in ways that are impossible for normal computers. Because of superposition and entanglement, quantum computers can process a huge number of possibilities simultaneously. This makes them especially powerful for certain tasks like factoring large numbers, simulating molecules, and optimizing complex systems. These are problems where classical computers struggle because they require too many calculations. However, quantum computers are not simply faster computers for everything. They are only better for specific types of problems. For everyday tasks like browsing the internet or writing documents, classical computers are still more practical and efficient. Quantum computing is more like a specialized tool rather than a replacement for all computers. One major challenge in quantum computing is stability. Qubits are extremely sensitive to their environment, and even small disturbances like heat or vibration can cause errors. This problem is called decoherence, and it makes building reliable quantum computers very difficult. Scientists use special techniques called error correction to try to protect qubits and maintain their fragile quantum states. These techniques require many extra qubits just to support one stable qubit. Because of this, building large-scale quantum computers is still a major engineering challenge. Quantum computing has many promising applications in science and industry. For example, it could help design new medicines by simulating how molecules interact at the atomic level. It could also improve materials science, making it easier to discover stronger batteries or more efficient solar panels. In cybersecurity, quantum computing could both create risks and solutions. It might break some current encryption methods, but it can also lead to new, more secure encryption techniques based on quantum principles. This is why governments and companies are already preparing for a post-quantum world. Companies and researchers are actively building quantum systems today, though most are still experimental. These early machines are called Noisy Intermediate-Scale Quantum, or NISQ, computers. They can perform limited tasks, but are not yet powerful enough for large-scale real-world use. As research continues, quantum computing is expected to grow slowly over time, much like classical computing did in its early years. Many experts believe it could eventually transform fields like chemistry, logistics, artificial intelligence, and physics. The full potential of quantum computing is still being discovered, making it one of the most exciting areas of modern technology.